Delhi and University of Queensland, and I am also the TA for this course. So let us begin the session for tutorial session for today. So in this way, that the classes uploaded in this NPTEL portal, they generally focus on three kind of laser: helium neon laser, argon laser, and dye laser. Although I have discussed helium neon laser and argon laser in previous class, I'll revisit them. So basically, this is the diagram of the helium neon laser energy transition diagram. Laser, and we know that what happened here, that helium and neon gases are mixed in the system here, and here the helium ions are excited to 2,3s and to 1s state, and they are being pumped, and then basically here between these two state, energy transfer, like from helium helium atoms, the energy transfer to neon atoms, and those photons then get emitted from E6 or 3s2. They simultaneously decay to 3p4, and from 2s2 they decay to 2p4, or from 3s2 they can go to the 2p4 also, and this those wavelength, the mentioned wavelength, they emit in those ranges. So basically the helium neon laser consists a long and narrow discharge tube, about 2 to 8 millimeter in diameter and 10 to 100 centimeter in length, which is filled with helium and neon with typical pressure of 1 torr. So helium s will at 1 torr and neon at 0.1 torr, and they are mixed, as I have mentioned, as 5:1 ratio. This is also the energy diagram I draw that day. So they are, and these are the steps that follow in this laser action. So basically, helium neon are at 5:1 ratio in the optical cavity. The actual lasing atom here are the neon atom. Helium is used for selective pumping of the upper laser level of the neon atoms. So when an electrical discharge is passed through the gas, the electrons which are accelerated down to the tube collide with helium and neon atoms and excite them to high energy levels. Basically, the helium atoms are being excited, then they transfer their energy. Helium atoms tend to accumulate at level F2 and F3. This is the F2 and F3 here marks. They are basically 2, 3s and 2, 1s. Like 2 is the orbit and 3 is so we have that is principal quantum number of the orbit, and they are the azimuthal quantum number of the um, uh, of the suborbits at 2. So they are given by n is equal to 0, 1, 2, and 3. So 0 means S, P means 1. That's the thing here. So 3 is 1s. So 1 means here the atoms like or the electrons are at this position, and 3 they are at the both are in the same like up or down. Here they are in the opposite direction. That is why this is 3, this is 1. So basically, helium atoms tend to accumulate at levels of these two levels, F2 and F3, due to their long lifetimes. And as E4 and E6 of the neon atoms have almost same energy of F2 and F3, that excited helium atoms collide with these neon atoms in the ground state can excite the neon atoms to E4 and E6. So after the helium atoms goes up to this 2 level, they have some longer lifetime here. So what happened when neon atom which are the ground level collide with them, they transfer their energy, and those neon atoms goes up to this 2 level E6 and E4, and they come back to the ground level. The helium atoms come back to the ground level. Since the pressure of helium is 10 times that of neon, the levels E4 and E6 of neon are significantly populate as compared to other levels of neon. The transition between E6 and E3, that this is E6 and this is E3, so the transition is between 3s2 to 2p4. This is the most popular transition. That means the wavelength emitted at this transition, which is 633 nanometer, is mostly used. Neon atoms de-excite through spontaneous emission from E3 to E2. So there is a spontaneous emission after that. Since the time is shorter than the lifetime of E6, so we can achieve steady state population inversion between E6 and E3. Where that goes. So there easily the population inversion has been created between E6 and E3. So the E6 has lifetime of 10 to the power 7 second. Minus 7 second, and E3 has lifetime of 10 to the power minus 8 second. You see that E6 has more lifetime, its lifetime is more. So it's easy to achieve population inversion in EX between E6 and E3. That E2 level is metastable level. It tends to collect atoms. The atoms from this level relax back to the ground level mainly through the collision with the walls. So they first come here. This is a metastable level. Then they go to the ground level here because of collision with the walls of the tube. And there is a possible that atom in this level to absorb the spontaneously emitted radiation in E3 to E2 to re-excite it. So from here they can go to E3, but that doesn't happen generally. The other two important wavelengths from the helium neon laser is 1.15 micrometer and 3.39 micrometer. And this 1.15 micrometer is corresponds to 2s2 to 2p4. In transition, we got 1.152 micrometer, and this transition between 3s2 to 3p4, we get 3.391 micrometer. Now you can see that, and 3s2 to 2p4 is 633 nanometer. Here that this transition and this transition both share the same upper level. Their lasing upper level is 3s2. Since they're using the same upper level and 3.39 micrometer, that lasing action corresponds to much lower frequency than 633 nanometer. The Doppler broadening is much smaller for this transition, and the gain depends on the like which transition have more gain depends on basically this factor nu square. The gain at 3.39 micrometer is much higher than the 6328 angstrom, 633 nanometer. Thus, due to this very large gain, oscillation will normally tend to occur at 3.39 micrometer rather than 630 nanometer. So once the lasers start oscillate at 3.39 micrometer, further build up a population in E6 is not possible. The laser can be made to oscillate at, so for if we want to oscillate the laser at 633 nanometer, we use optical elements in the path which strongly absorb the 3.39 micrometer wavelength, or increasing the line width through the Zeeman effect by applying an inhomogeneous magnetic field across the tube. So that is basically a helium neon laser in a nutshell. Those things here. Now we come to ionic laser. This is ionic laser in nature. So basically, the argon ion laser. Uh, Here the electric field has been uh, electric field or the pumping has been done using those electric field. They are not placed at the end but on the sideways. The most popular wavelengths for the argon laser is 458 nanometer, 488 nanometer, 514 nanometer, and 351 nanometer. The basic construction features are similar to the low pressure gas discharge laser, except that here solenoidal spiral is around the discharge tube to all but low power argon ion lasers here. So the electromagnetic coil put across the plasma tube generates a strong magnetic field, includes in longitudinally along this axis. So this purple color thing are the electromagnetic field. And that has been generated by electromagnetic coil. This essentially increases the current density by keeping the electrons and ion near the center rather than allowing them to collide with the walls of the discharge tube. And if we control this thing, then the unnecessary heat generation will be the less. So the here what happened that argon neutral argon lasers here, it has been showed at the inside that argon, this is the argon ground state at 0, and that this is argon plus ground state, and here apart from this level, which is more than 305 electron volt, lasing actions happen. So basically what happened, which is argon neutral atom of argon collide with the electron with kinetic energy. So that first create argon plus, which is an ion, and an electron. And this electron will have less kinetic energy. Then this argon, so from this it goes to this state, argon plus ground state. Then the electron collides with argon plus ion. So I am writing here kinetic energy. This kinetic energy and this kinetic energy may not be the same. So that will push argon plus ion to upper excited level. Electron will have less kinetic energy. And from that state, it will emit photon, which is a spontaneously emitted photon. That will come to this state, which is E1. From that upper excited argon, let us suppose here argon plus excited state to E1, lasing emission happens between those states, and that from E1 to argon ground state, we get another non-radiative transition. So depending, and if this is the case one, second case, no, actually this is the case one. And if we need the ion, like if we need laser action happening in a deep UV region, we need doubly ionized argon ion. So that case, what happened that it collide with another electron and makes argon 2 plus in the ground state and emit an electron and emit and the same electron with which it has collided will have now less kinetic energy, and then this argon plus plus will again collide with another electron and it will send it to upper excited level. So depending on this upper excited level, we get four kind of emission from this laser. So here, here, there's two kind of schematic basically. So in schematic one, we can first I need to write this the color of this wavelength. So this is blue. This is blue green. This is green, and this is UV. So for this we need argon plus plus, and for this argon plus is sufficient. So we can put the preser or dispersive element inside the cavity or outside the cavity. So if we put outside the cavity, so you see that the laser is got dispersed, and we can have multiple output lambda 1, lambda 2, lambda 3. But if we want to choose one lambda only, so we put that prism inside the cavity, and the prism is placed such a way that it only allows lambda 1 to get amplified inside the cavity, and only we will get lambda 1 as the output. So these analyzers can be used as a first, this has been used as a first atomic clock, and that is not argon ion laser, but some kind of ion laser that has been you that has been sent to acclimation in the moon. And because of this thing that we are using argon gas, which is a neutral gas in general. So the wall plug efficiency of this laser is very low. Can be between 0.01% to 0.001%. So argon ion laser discharge is very intense, typical values being 440 ampere at 165 volt. A particular wavelength, as I mentioned here, as can be chosen by dispersive prism. Rotation of this prism mirror system provides feedback only at the particular wavelength which is incident normally on the mirror. So this mirror can choose a wavelength, but the correct way to say this, that using this mirror we can choose a wavelength that can fall normally on the mirror, and that will get amplified because of continuous feedback at each round trip the argon laser operate basically. And the argon ion laser can operate at 3 watt to 5 watt. So that its wall plug efficiency is 0.01%. So you can imagine how much power it needs to generate 3 watt efficiency. Then I'll discuss another gas laser which has not been discussed at the class, but for the sake of complexity I'll mention. That is carbon dioxide laser. In carbon dioxide laser, one uses the transition occurring between different vibrational state of the carbon dioxide molecule. So, last day I was discussing that gas laser can be atomic laser, ionic laser, and molecular laser. So, helium neon is basically atomic laser. Argon laser is the ion laser. Carbon dioxide laser is the molecular laser. So, here you can see the 3 independent modes of vibration of the carbon dioxide molecule. So, here at the center of mass, there's carbon. These 2 oxygen can vibrate along this way. This is the one way, and they can actually, this is not how actually carbon dioxide is not linear. It can bend like this. Different. So when bent, if the oxygen molecules vibrate along this line, that's another state of vibration. And another state of vibration that the carbon is also vibrating and oxygen is also vibrating. So basically, as the carbon is vibrating, it happened that oxygen is not vibrating on its own, but its position is getting changed, and it also can happen the oxygen is also vibrating along with carbon. So this is the 3 independent modes of vibration of the carbon dioxide molecule, and because of this, they can have different vibrational states. So this is called stretching. This is bending. And this is asymmetric stretching. Each of these modes is characterized by a definite frequency of vibration. According to this quantum mechanics, this vibrational degree of freedom are quantized. So when a molecule vibrates in any of the modes, it can have only a discrete set of energy. Thus, we know the energy is given by this equation, and if it's vibrating with frequency nu1, so energy will be E1, and M can be 0, 1, 2, 3 So if we assume that mu1 is the frequency corresponding to the symmetric stage mode, then a molecule have only energies at this level. And there is a case that carbon dioxide molecule can vibrate in combination of the three modes, and then the energy will be defined by so energy will be vibration can be described by these three integers m, n, and q. So the quantum number then will change to m and q. So the laser transition here occurs between E5 to E4, that is 10.6 micrometer. This occurs between 001 to 100. So basically, it's between when the m is 0, n is 0, and q is there. So you basically the asymmetric stretching is being there, and 100 corresponds to the symmetric stretching is there, but n and q is 0. So between those two levels, so we put amount of carbon dioxide and nitrogen gas in the carbon dioxide laser. So some carbon dioxide molecule can vibrate in symmetric stretching, some can vibrate in according to asymmetric stretching. So basically for this reason, this transition can happen between E5 to E4. And some amount of helium gas is also present in the system here, in carbon dioxide system. So carbon dioxide is to N2 is to helium ratio is 1 is to 4 is to 5 basically. So we have also seen that in helium neon in the helium neon laser also, so it is 10 is to 1, that is the ratio between them. And also you can see that none of them are tunable laser. Like if you count that argon ion laser is giving you 4 wavelengths and you can choose one that is tunable, that is actually not tunable. Here also that the carbon dioxide laser is basically 5 level laser. It can give 10.6 micrometer lasing and 9.6 micrometer, but they are not tunable at all. That's why we needed, because of this, basically laser was not being, scientists was not being able to use lasers even after the discovery of the lasers, because for spectroscopic reason, like it is wrong that scientists were not able to use the laser. They are not able to use the laser for spectroscopic reasons until we get the tunable lasers. And here the E5 is the long-lived um, long-lived energy level, because the positional transfer from merely resonant excited nitrogen molecules. So they basically the nitrogen molecule transfer energy to carbon dioxide. So they resonate in the same energy levels. The carbon dioxide lasers are very efficient. They are 30% efficient. And the reason is because efficient pumping to 001 level. And also because all the energy levels involved are close to the ground level. So you see the energy, the upper laser level is 0.3 electron volt. So the pump energy required is not that high. So the quantum efficiency ratio for that 10.6 micrometer transition is basically E5 minus E4 by E5 minus E1. So that is quite high, that's 45%. But we also need to think that uh, the all the transitions in the carbon dioxide laser are not at that. Some of the transition will be 9.6 micrometer, then optical cavity will choose this transition and amplify this transition. So that's the reason we say that about 30% of the quantum efficiency is about the 35%. So where did carbon dioxide lasers have been used? So basically they are using welding, hole drilling, cutting, etc. And they also used in open air communication. So they are all the gas lasers. Now we will go into the basically the liquid lasers. And why do we need liquid laser? First, we need to know that. Because of tunability, like spectroscopic studies needs tunable laser. So for tunable laser emission, we need a broadband energy level. So, and all the energy levels, like the upper laser level needs to consist some of the more than one energy level. The lower lasing level also needs some of the more than one level. So basically, we cannot just depend on electronic transition. So we also need vibration and rotational energy levels. And we know that atoms cannot have vibrational and rotational energy levels. What having to have a vibrational and rotational energy level, we need molecule, because atom and ions have purely electronic transition. That's the catch here. So we need vibrational and rotational level associated with the electronic level, and those vibrational and rotational level has to be closely spaced. So dye laser come here to solve this situation. So the dye lasers are the liquid lasers. So organic dye compounds, they are being uh, dropped in their liquid solution. Uh, so that can be ethanol, methanol. Benzene, acetone, and even water. This solution is used as the active medium here. So here a flash lamp. So this is the energy state. This is the energy levels. of the dye lasers. So basically S0, their singlet state, S0, S1 and all. And triplet states are mentioned by T1, T2. So singlet state, basically what is a singlet state? Basically there the electron orientation are in opposite direction. So the spins of the electron, so when I say electron orientation, they are basically spin of the electron. The orientation are in the opposite sign, opposite way, and they cancel each other. But in the triplet, they are in the spins are in the same direction. So that's how it gets divided between singlet state and triplet state. And the ground state, that is usually a singlet state, and there is no T0 state. So triplet states start from T1, T2, and singlet states start from ground state, that is from 0. So the capital S is S1 plus S2 to S1 minus S2. They are the spin of the electrons. So small s1 can be half, plus half, and minus half, and s2 can have plus half and minus half. Similarly. So s1 plus s2 maximum value, it can have 1. And the minimum it can have, so you can have minus half mod also, that will also give 1. So the minimum it can give you to 0. So basically this is the electron spin orientation can have the same direction, maybe it be up or down, but it is the, for singlet there is one orientation, one is up, another is down. You can write down first and half first. They will differ quantumly, but their energy will be the same. So what happened here that when we gave the pump energy, the pump can be a flashlight or can be a UV laser, whatever is being used. We will discuss that later. What happened, the molecules which generally reside in the bottom of the singlet ground S0 state. So when the pump is given, they transition to different S1 state. And from different S1 state, they come back to the S0, different level of the S0 state. So S0 are a combination of different energy levels. So and S0 and as S1 both have multiple closely spaced multiple energy levels. So let us assume there are different states. Okay, here there is splitting is different. So one atom goes up to that state, and from there that goes here. So this is lambda 1. You can see another level that from here it goes up to there, and from there it then goes. This is lambda 2. Lambda 3 can be like this. It's lambda 3 and so on so forth, lambda 1, lambda 2, lambda 3 and different wavelength level. So as they are very closely spaced, the difference also that like this energy level, this energy gap give you a lambda 1, this energy gap give you a lambda 2, and this is lambda 3. The lambda 1, lambda 2, lambda 3, they are also close to each other. So these are I'm talking about spontaneous emission at first. Noise emission. So after spontaneous emission, we are getting lambda 1, lambda 2, lambda 3, lambda 4, lambda 5, and so on and so forth. Now, if we put this molecule or the not the molecule, the dye mixture inside a cavity, optical cavity. So here the dye mixture, the optical, put in an optical cavity, and we selected that optical cavity length such a way that only one lambda 1 get amplified due to feedback and other lambda 2 lambda 3 doesn't have a gain above loss line, then we can get lambda 1. Now if we change the length of the optical cavity, maybe we'll get then lambda 2 and lambda 3 and so on and so forth. So basically for spectroscopy, if we are going to use different laser for different wavelength, then spectroscopy would have been a very like expensive affair. But we are using tunable lasers in case of spectroscopy. So different wavelength can come out from a single laser. So this makes easy the spectroscopic study of different material, this kind of tunable laser. But so this we can say dicer. So this is one of the So this is the schematic illustration how the dye laser works. So here you can see that the dye solution has been put between an optical cavity and they are in the transparent dye cell. And here the side pumping has been used. So it can be pumped either using a flash lamp or another laser. First time when it was like in 1966, it has been invented. The ruby laser was used as a pump source. So for low power operation, it is not mandatory, and the side pumping has been achievable. Uh, and the pump light passes through in this arrangement. Okay, and a beam expander is being used for a intense output. So for low power operation, we don't need to flow the heat. Heat dissipation is not mandatory. But for high power operation, we need to remove the waste heat to prevent rapid dye degradation. So here a laser light has been used, but if we use laser light as a side pumping, there is no problem. But if we use flash lamp as pumps, we would need in cylindrical reflective arrangement so that the pumping is efficient. Another thing is basically if we need to generate a red light, we need it to pump the green light here. So the harmonics needs to be used in terms of frequency of the pump laser. So like the green has less wavelength, so we need to have a wavelength for pump source which have higher frequency than we want to obtain. But there is also problems here. The first problem is here. There can be a crossover. Some molecules from S1 can go to T1. So that will lessen the population inversion. And another thing is that, so when the molecules got to T1, so that will diminish the population in that can actually not that will that can diminish the population inversion, and we will get less lasing action if some molecules go to T1 from S1. And another problem is that it's a metastable state. So the probability of the molecules coming down to ground state that and probability the molecules that can go to the upper triplet state, like the probability of absorption is high enough. So in that case, there will be that is a sinking operation inside the photon sinking operation inside of the laser. So in the laser, it is photon source, it cannot access a sink. So if that happens, that the molecules who go to the T1 state, they are absorbing another photons, but they can absorb this laser photon as well, and they can absorb this laser photon and go up to the T2. Say so the basically the splitting of this level, or the very closely spaced vibrational and rotational level, which help us to get the tunability of the laser. It can also, like, we get the tunability because the any like molecule present in any level can absorb photon and go up to the any level of the upper lasing level, and they can come down and we will get a lambda 1, and if the levels change we get another lambda 2. So endless possibilities of or combination of absorbing light or pump. But here also it acts as a con when that any energy you generate from the lasing state, the molecules at T1 state can absorb that energy and go up to the upper triplet states. So here the source of a photon and sink of the photon is in the same medium. So to prevent those, we use some quenching agent. So this effect gonna be less. So more or less, this is the working of the dye laser. So the most question from this part is most of the theoretical question. There are very less numerical question, and numerical questions can be of like the estimate of the Broadbent line width of carbon dioxide laser at temperature 300 Kelvin, but Dr. Broading has not been discussed in our class. Or line width, so that has not been discussed our class. So most of the quiz question is in theoretical in nature. So I'll discuss some quiz question, previous year quiz questions now. So the question number one is, single longitudinal mode operation of helium neon laser is achieved generally by options are A. Reducing the operating pressure, increasing the operating pressure, C. Increasing the transmission loss of the cavity, decreasing the transmission loss of the cavity. So the longitudinal modes spacing are given by C by 2L in the laser cavity. To achieve single mode operation, we basically, there is a gain curve. So actually this is so this is the loss line. And we know the cavities are like modes are like this. So for single mode operation, basically single mode operation means only one mode will cross the gain line or the threshold gain. So if we increase the transmission loss such that only one mode closest to the peak has the gain that can cross the threshold, we will achieve the single mode uh, operation. So the right answer is increasing the transmission loss of the cavity. If we decrease the transmission loss, then all the cavity will be the have the gain. Question 2. An ion laser can operate at ultraviolet frequencies because outermost electrons are involved in the lasing process. Inner electrons are involved C. Ground state doesn't exist. D. None of the above. So basically, we will know E is equal to H nu. So nu, delta nu is basically delta E by H. So for ultraviolet region, means we need high frequency. So the high frequency we will get when the transition occurs between the inner electronic energy level. So the inner electronic energy level have large energy separation. And for ultraviolet region, we need high frequency. That means high energy separation. So the answer is inner electrons are involved in the lasing process. Question number 3. Ion lasers have lower wall plug efficiency than atomic lasers because If it doesn't fill in the blanks, the most appropriate answer would have been because some of the energy goes into making the ion first. But it is a multiple choice question. So see, let us see what are the options. They are optically pumped, B, there is more heat dissipation, heat dissipation. C, they are end pumped. D, none of the above. So, as I have said, that this is the efficiency, output power, optical output power versus electrical input power. So some of the electrical input power goes into that ionization. So for that they need very high discharge current. So because of this high discharge current, significant heating is there. So this is the answer. There is more heat dissipation. They are end pumped. That is not an sure and like that is not a reason why ionizers have lower wall plug efficiency. Atomic lasers are also end pumped, and gas lasers are not optically pumped; they are electrically pumped. So that is why the correct answer is there is more heat dissipation. Question 4. Emission from a free running argon ion laser A comprises of multiple wavelengths. B is generally SLM. C has a single wavelength. D SLM and single wavelength. So we know from the literature that argon laser, argon ion laser can emit 4 distinct wavelengths. So single wavelength is not the answer. Is generally SLM, doesn't need to be. So the correct answer is it comprises of multiple wavelengths. That is the correct answer. Question 5. This divergent laser emission can be obtained by A. Reducing the tube diameter, B. Increasing length of the cavity, C. Reducing length of the cavity, D. Increasing the tube diameter. So for the Gaussian wave divergence theta, given by lambda by pi omega naught. So the omega naught is the beammost. So for less divergent, theta should be less. So better mode confinement we need. So this is so if we optimize or reduce the tube diameter, it improves the spatial mode control. And so basically this equation doesn't need. So increasing the length of cavity doesn't do any good. I mean, the length of cavity has not that much of effect on the divergence. So the divergence depend on the beam diameter, and the beam, if we reduce the beam diameter, we will see the better divergence. So for that reason, this is the answer, reducing the tube diameter. Question 6. Liquid lasers are more tunable than gas lasers because liquid lasers operate at lower temperature, providing better emission spectra. Use dye solutions which have broad spectral range. They produce more coherent light compared to gas lasers. They are less affected by external pressure. Pressure and temperature changes. So we use, so the tunability is because they have more vibrational and rotational energy levels. So basically, in other words, they have more spectral range or broad spectral range. This is the reason we use liquid laser for tunability, or they are tunable. The lower operating at lower temperature doesn't give the tunability. Tunability when it gives, if you have scope closely spaced different energy level, so that we can have different wavelengths by adjusting the optical cavity length. Temperature pressure has nothing to do with it. Like it may, like it, controlling the temperature and pressure may give better tunability, but to have tunability, we need to have a broad spectral range first. Question 7. Triplet states in dye laser. Option number A. Aid in selective pumping. No, not. true. B, have a very short lifetime. That is also not true. That is a metastable state. C, acts as absorbers of laser radiation. D, has no effect on the laser performance. It has effect, and I have also discussed that it absorbs some of the laser radiation. So that is the triplet states do. But if you add some chemicals, then maybe the D is the right answer, that it has no less effect. No effect is not the right answer. It has less effect on the laser performance. Question number 8. Punctures in a dye medium. A. Enable populating triplet state. No, it doesn't enable. Its main thing is to depopulate triplet state. B. Act as scatterers in lasing media. C. Depopulate triplet state. D. Increase self-absorption of laser emission. Why would we increase self-absorption? So the answer is depopulate triplet state. We have discussed that earlier. So that is for today. We'll discuss in the next class about the solid state laser.